Hello, 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 hello. Okay. Hello. I hope my audio is clear. Just testing out the Zoom whiteboard feature. Um, since 1 second, some network issues. Hello. Uh, okay. Sorry for the delay. Just give me 1 minute. Let me test this whiteboard out. And yeah. Mm, I just want to see the notes are visible. Mm, right. Mm, Unfortunately, doesn't even- okay, okay. Yeah. The reason I'm using whiteboard today is some issue with Zoom, because of which there is echo when I'm sharing the screen and like not being able to do it. So I'll try this today and share the notes later. Um, right. Okay, I see only one participant, so I'll continue. Um, so any questions? So if you have doubts, I'll answer that directly then. Can you hear me? Yeah, if you have any doubts, maybe since only you are there, so we can discuss your doubts. Otherwise, I'll cover everything. Okay. Can you confirm if you can hear me? One second. Okay. Um, so Let's begin. Could you type yes in the chat if you can hear me? Fine. So, let's carry on. So today we'll be discussing many, like mostly two things. So the first thing that we have to discuss is DSSS um, technique. So we had discussed this last in the last week's the last week's like discussion as well. But there are many questions in this week, so I'll just kind of quickly revise what it was, and we can just go directly to the questions. If you have any doubts, please let me know. So you can get some question like this that so this is um, you're told that bandwidth whereas let's say that your spreading factor sorry 1 second spreading factor which is q. So this is in a DSSS system. Spreading factor q is said to be 32, right? And uh, symbol time is it's these numbers above. This is let's say 16, and symbol time is 2 microseconds, right? So you are asked uh, what is the bandwidth? You are asked what is the bandwidth of the resultant system? Bandwidth of the resultant system, right? So, so we know that like for normal, for without, I hope you can hear me. So we know that without DSSS, without DSSS, what is the bandwidth? Bandwidth is 1 by TS, which is half, and this is in microseconds, so this will basically be 1 by 2 megahertz, right? Half megahertz. So this is without this technique. Like if you're just using normal frequency domain, like if you're just using normal sampling and seeing the signal in frequency domain, this is what you'll get. But with DSSS, what happens is, as we know, bandwidth is 1 by TC, which is Q times the original bandwidth. Or, so, so we know that the bandwidth becomes Q times of B. So Q times B. So this is half times 16 megahertz. So the answer is 8 megahertz. So that is the bandwidth of the DSSS signal. I hope this is clear. So this is very simple. That you take bandwidth of original signal and then you just because bandwidth gets multiplied, you just multiply it with the spreading factor, right? And so let's say you are also asked chip duration, right? You are also asked, or you can be asked a reverse question also. So from here, let's say you are asked what is the chip duration. Chip duration Tc. As we know, chip duration is nothing but the symbol duration divided by the Q factor. So symbol duration is 2 microseconds divided by 16. So that is 1 by 8, that is 0.125 microseconds. It's a chip duration. So now you can also be asked an opposite question where you are given, let's say you are given, my bad. You are given TC and you are given Q. And then you have to find TS. TS and the signal. So you have to find TS. So this also is doable because TC is equal to TS by Q. So TS is equal to Q times TC. So it's just a multiplication. You're given the chip duration and you have to find TS. So symbol time. So that is nothing but Q times TC. So you just have to plug in the two values and you are good. Okay. Uh, so this was very simple question. Another related question is with regard to Fourier transform. Right, Fourier transform that is used in all of this, like DSSS spectrum. So if you're given a rectangular pulse, right, something like a rectangle of t minus tau divided by capital T, then you are asked what is the Fourier transform of g of t. Right? You are asked what is the Fourier transform. Now we have to use the Fourier transform properties here. Okay. First property is, if we know x of t has some signal x of t has a Fourier transform x of f, this means that x of t minus tau has a Fourier transform of x of f e to the power minus 2 pi f tau, right? So this is one first property that we keep in mind. Now, and then we know that this rectangular function, rectangular function of t by t. So this function has a Fourier transform of capital T, same function of ft. This is a known Fourier transform, can be derived, but like this is basic. It's known that rectangular function has same function as its Fourier transform. We know sinc function, I guess. Sinc of x is, in electrical domain, we write it as sine pi x upon pi x, right? So this is not bad. He's trying to. So then let us combine these, right? So if rect of t by tau has this Fourier transform, then rect of t minus tau by t. So if we combine these two, is equivalent to, and so this is my actual pulse g of t. And so what I'm trying to find is capital G of f. And so we know, so let us say this is some x of t and this is the capital X of f that I have, right? So this is what I'm mapping. So x of t is this. So this is capital X of f. Now I have x of t minus tau, right? So this is like x of t minus tau. So this is x of t minus tau. And so using the formula, so this will be capital X of f. So this will be t sinc function of ft, and then e to the power minus 2 pi f tau. So that is the answer of the Fourier transform. Okay, that is the answer of the Fourier transform. I hope this is clear, right? Okay. So this is Fourier transform, and now the question is, now that we have the Fourier transform, we want to find out the points where we want to find out the roots of this, right? We want to find out the points where g of f, mod of g of f is equal to 0, right? At what value of f? So let us see. So what is mod g of f? So this part, this term, e to the power minus j, actually, 1 second. This is, yeah, I missed something. This, I missed the iota. So this is e to the power minus j 2 pi f tau. So everywhere this will be there. So we know that e to the power minus j theta has magnitude 1. So the modulus is nothing but this quantity. This quantity. Right? And so what do we know about this sinc function? Sinc function is 0 at sinc function is 0 at odd values, right? Or like at integer values that are not 0. Right? So sinc function will be 0 because see sine pi x by pi x. So at any integer value other than 0, so 0 is the limiting case. So we have to take 0 by 0, we have to take a limit and it comes out to be 1. But other than 0 at all integer values, sinc function is 0 because sine n pi is 0 for all n. So let's write that sinc of x equal to 0 for all x belongs to integer other than 0. Right? So I hope this makes sense. So actually what we are looking is for first 0 crossing. First 0 crossing. What do you mean by first 0 crossing? Because as I said, sinc function at 0 is 1. Actually, it will be t here. It will be. So this is the mod g of f gain function. And at small f equal to 0, the magnitude will be t. And then it will drop to 0. And then it will rise again and drop to 0. And this way it will continue, right? So that's how the sinc function looks like. And so we have to find out this point, first 0 crossing point, let's say. So what will be the first point here? If we want the positive direction, then it has to be, basically we need ft equal to some integer, right? And what can be the smallest integer? It is 1. Smallest integer is 1. So then, and so this is the point f critical. So smallest integer is 1. So fc will be equal to 1 by capital E. So this is my first 0 crossing point. This is something that we had discussed in previous week's content also. Just like very clear. I hope this one is clear. So this is again regarding the DSSS segment. Okay.
Hello, sir.
Yes.
Can you please repeat again? That's the 0 crossing. Just
Yeah, zero crossing. Okay. So you understood, hopefully you understood this argument that sinc x equal to 0. So what is sinc x function? Sinc of x, again I'm writing, it is
sine
sine of
pi x by x.
by pi x.
Pi x.
Yeah, sine pi x by pi x. So when will this be 0? Because like denominator, this will be 0. One case where it will be 0 is when x goes to infinity, because then sine is a bounded function between 0 and 1, between -1 and 1. And then your but x will be unbounded, so then this, like it's bounded divided by unbounded, it goes to 0. But then in the bounded regime, when does it goes to 0? When the numerator is itself 0, right?
Yeah.
So this equal to 0, this means that typically sine pi x equal to 0. And when is sine theta equal to 0? When theta equal to n pi, right?
Yeah.
So then you will have pi x equal to n pi, and which means pi, you can cancel out pi, so x equal to n, where n typically can belong to any integer, but we'll have to leave out 0.
Except 0. Except 0.
Yeah, because at 0, what happens is both numerator and denominator are 0, so
But
that's
it
a
go to
limiting.
infinity. Infinity. Infinite.
Yeah, it's not infinity, it's actually 1. Like you have to take limit. So that is why you get this thing, right? Limit x approaching to 0, sinc of x.
That is 1.
Yeah, so you have to use the L'Hopital rule. You have to take derivative numerator and denominator. Sine derivative is cos, so pi cos pi x. And so this comes out to be 1. So at 0 it is 1, at all other integer points. So that is why you have this distribution, right? So at all other integer points, you will have value 0. So that is why then this will be, so you have to take here, from here you have to take all x that belongs to a set integer or z oblique 0. So you have to leave out 0. So in that case, your first 0 crossing point will be when x is equal to 1.
Yeah.
Right? So in this case, x means ft is equal to 1. So ft equal to 1 means f equal to 1 by t. So that is your first 0 crossing point. Is this clear?
Yeah, okay.
Okay. So that is Fourier transform. Now, I don't think there are much more problems. But now we'll have to discuss a different topic, which is random sequences. There's some questions on there are some questions on CDMA and WCDMA and all that, but it's mostly very textbook. So like it's straight from the lectures.
Sir, can you do one thing? That can you explain your shift register?
Yeah, that is I'll explain that.
M sequence shift register.
Yes, I'll explain that. One small question is there. I'll just do it before going to M shift register. That is the most important topic. I will talk about it. But one small question is there. Let me finish this quickly.
Yeah.
So you are given that like you have a CDMA 2000 system, right? And so in CDMA, what happens is base stations are given some codes, unique codes, and so codes. Let's say you are told that codes are separated by some 16n, where n belongs to I. So let's say your first base station is given code 0, second is given code 16, third is given code 32, and so on and so forth, right? Sorry, so we don't know the value of n here. So let us put n equal to 1. which means that codes are separated by 16. So first base station is base station 0, second is 16, and so on. And length of codes, length of short codes used equal to sum 2 to the power 10. So you have like the 10 bits, let's say, to denote your code. And so you can denote possibly 2 to the power 10 numbers. And over there, your separation between base stations is 16, right? So your question is maximum number of supported base stations. So what is the maximum number of base stations that you can support? And so this question is very simple actually. So you have 2 to the power 10 numbers. So let's take a, like, forget this these big numbers. Let's take small numbers. Let's say you had 100 numbers, and you are told that you have to pick pick unique numbers that are spaced at interval of 10. So how many can you pick? So you'll pick like 0, 10, and so on till 100. So on till actually the last one that you will pick is, the last one that you can pick is 90, right? And so that is 10 numbers. So you can pick 100 by 10 equal to 10 unique codes. So, and then, you can give the first code to base station 1, second code to base station. Similarly, in this problem also, maximum number of base stations is the total length of codes that you have. So you have 2 to the power 10 codes to assign. And you have to keep a gap of 16, that is 2 to the power 4, between two base stations. So you cannot overlap codes because you want to avoid interference. So you have this 2 to the power 4 gap between base stations. So that leaves you with 2 to the power 10 minus 4, 2 to the power 6. 64 base stations can be supported in this CDMA system. So this kind of, because this one question, similar question was there. So if I covered this, it's very simple. The idea was very simple, right?
Sir, one thing that at this time we have to assume what is the value of n. Here we have assumed that n is equal to 1. That
So that is always given in the question. If you see in your assignment as well, the value of n is given.
Okay.
Fine. Let's see. Okay. So now let us get into convolutional codes and how to work with convolutional codes. But before that, there is this. We will get into that later. Before that, let's do this relatively simple problem. It's also there, like similar to this is there in your assignments. So you have this kind of a system, right? You have some data coming in at rate R1, and you have a convolutional coder. So, and then you have the output with rate R2, and then on top of it, you have a spreading system, right? 2 equal to 32, let's say. And your final output is R3. So this is your coder. So you are first doing convolution coding. And with a certain rate. And then you are using a spreading sequence and finally transient. You are told that R3 is equal to something like 1 second. One second. Let me just quickly do a calculation. Um, 32. So you're told that R3 equal to 640, right? 640 K ports per second, kilo ports per second. That's the unit. Because ultimately, if you're using a spreading sequence, you are actually kilo chips per second. Because in spreading sequence, if you remember, what you take input is bits and then you output as chips, right? Because you are kind of outputting the chipping sequence. Like you chip off the original signal and you output something like 640 kilo chips per second. So now you are told that input rate R1 is equal to 5 kbps, right? 5 kbps. So question is, so these two information you are provided. Question is, and this is, and also another information you are provided is just length of the spreading scheme. So you are asked what is the rate of the convolutional coder. So I'm not going into the mechanism of how a convolutional coder works or not, but this is a more simple notion that what is the rate of the convolutional coder. So this kind of a problem is there. So it's actually pretty simple to do, even if you don't understand convolutional coder fully. That's why I thought I will just discuss this. And here's the thing. So let us figure out what we know first, right? We know R3, we know Q. Can we get R2? We can, right? Because if you remember, like in DSSS, in the spreading spectrum scheme, the bandwidth is actually multiplied by Q. So bandwidth is same as the rate. So rate is also multiplied by Q. Rate is also multiplied by. If you remember that the amplitude becomes 1 by Q square, and the bandwidth spreads out by a factor of Q. Nice. So that kind of thing. So if the output rate is 640 kilo chips per second, which means that R2 before the spreading sequence, it was R3 by Q. Because after spreading, the bandwidth spreads, the rate becomes multiplied. So before spreading, we'd have to divide it. So 640 divided by Q, which is 32, it comes out to be 20. The units now will be kbps because we are feeding signal in bits, right? We are feeding signal in bits and we are giving output in chips because we are using chip sequence. We are feeding signal in bits and we are giving output in chips. We are using chip sequence. So from chips, we have come to bits domain now. And so now from 5 kbps to 20 kbps, so we know that how does a convolution coder work? Convolution coder works like, let's, so for 5 kbps, we are getting output as 20 kbps, which means that for every bit that is being sent as input, we are having 4 bits as output, right? That is how a coder works. So you have some code rate. So code rate, let's say R is equal to 1 by 3. What does this mean? That one bit input results in 3 bits of output, right? That's how a coding system works. So you have some interleaving, some parity bit, whatever, and uh, okay, and so in this case, let us find out. So we know R2 and we know R1, right? So let us find out R2 by R1. So R2 is 20 kbps and R1 is 4 kbps. Actually, let us do it the other way. So the coding rate, uh, so this was an example. This was just for example. In this case, code rate, actual code rate, R is nothing but R1 divided by R2. So that will be 5 by 20 equal to 1 by 4. Right? Because for every one bit that is being input, the output is 4 bits. So that we should remember that. So this is how you actually calculate the coding rate. So if you, so as I'm seeing on my other device, if you're having difficulty viewing my whiteboard, you should zoom in and zoom out. I am not sure how you are viewing it, but you should try zooming in and zooming out by yourself also. If there is some resolution problem, right? But code. So I hope this was clear, right? That so you have this kind of a question where you are provided a full system. So from input, you are passing it through a convolution coder, and then there is a spreading sequence, and then you get output. You are provided output rate, you are provided input rate. You have to figure out the rate of the convolution coder. So you have to do some calculation. You have to calculate this intermediate rate, and then check that what is the ratio of the input rate to the intermediate rate, and that is your code rate. Because for every 1 bit that you are sending to this coder, you are getting 4 bits out of it in this question. Right. Okay. Let's continue. Hope everybody followed. Any doubts? These parts were relatively simple. Now let us try this kind of question. Let me do another small question first. So you are asked, there is this notion of primitive polynomials. In Galois, in something known as Galois field 2 of the order 2. Let's say one question can be, you want to find out if this polynomial 1 plus x to the power 4, sorry, let me just change it. You want to find out if 1 plus x cube is primitive or not. Now, how do you define a primitive polynomial? It's very in Galois field 2 especially. So this is a little bit of mathematical, but it's important to understand this notion. By Galois field 2, all we mean is just two numbers, 0 and 1. So essentially this is binary arithmetic. What I'm trying to say here is that when I say that x belongs to Galois field 2, right? When I say that x belongs to Galois field 2, what I'm trying to say is like x is a binary number. And so what we are trying to figure out is, let's say this is some f of capital X. So we are trying to, so by primitive, two things are there. primitive one is f of x is irreducible, and I'll come to what it means. Irreducible means there is 1 second. Just 1 second. Some issues there. Sorry. Yeah, I think this is fine now. Yeah. By irreducible, it's essentially there is no factorization is possible. No factorization. And second is that this thing, roots don't belong to Galois field 2. So we have to check for these two. Like, can we factorize this polynomial f of x, and does it have roots belonging to Galois field 2? So the second thing is easily checked. In Galois field 2, we have two numbers, 0 and 1. So let us find out f of 0. F of 0 is 1 plus 0 plus 0, it is 1. So this is not equal to 0. So 0 is not a root. Let's find out f of 1. It is 1 plus 1 plus x cube. So 1 cube, that is again 1. So 1 plus 1 plus 1 is, in binary arithmetic, it is 1 again. 1. Right? This is binary arithmetic. So in binary arithmetic, this is 1. So this is again not equal to 0, which means that 0 and 1 are both not roots. Right? So this is 1. So this condition is satisfied. So roots don't belong to Galois field 2. Right? Now, question is this reducible? Can you like factorize this thing? Let us try. Once second. Apologies. So f of x is 1 plus x cube. Now, so in binary arithmetic, what we know is for any two values, x plus x is always equal to 0, right? In binary arithmetic, because 0 plus 0 is 0, 1 plus 1 is also 0. Right? If you add 1 and 1, then it again goes back to 0. So, using that notion, let me just add x square and x square and see what happens. Because essentially this is no difference, right? We can always add x plus x. So this thing is actually adding 0, so it makes no difference. Let us see if we can break this, right? And it doesn't look like we can break this thing. Because 1 plus x times 1 plus x plus x squared times 1 plus x squared, right? Sorry, it's x squared times 1 plus x. So this is the factorization that you get. And so it is 1 plus x times x plus x square. This is not really factorizing. So, yeah, I don't think so. This is 1 plus x. 1 plus, you can take 1 plus x dot 1 plus x. And so you can try all kinds of juggling, but you will see that this doesn't, so there is no factorization, right? This is still, I don't have something like fx equal to some f1x times f2 of x. Right? I'm not being able to separate into factors. So you can try these kind of things and see and say that fx is irreducible. So there is no factorization possible. You cannot have factors. So that's why this function is not factorizable, not reducible, and roots don't belong to value of L2. So that is why we will call this, this is a mathematical notion, we'll call this a primitive. So the answer to this is yes. So this is a primitive function, 1 plus x2. So similarly for other examples in the, like other examples in the, like in the assignment, you can try and see if you are able to break into factors like this. Right? Okay. So, so this is a primitive polynomial.
Sir, excuse me, sir.
Yeah.
Sir, why it is primitive?
It is just definition. Like definition of primitive function is that you shouldn't be able to factorize it, and it shouldn't have any roots that belong to that is either 0 or 1. So second condition we check very easily, that there 0 is not a root, 1 is not a root. So second condition is satisfied. First condition checking requires a little bit of trial and error with algebra. That so this kind of tricks you will have to use. So here you can see that x to the power 0 is there, 1 is there, x to the power 2 is missing. So you just add it in this way, that x plus x is equal to 0. We know that in binary arithmetic, that 0 plus 0 is 0 and 1 plus 1 is also 0, right? So you can write x plus x equal to 0. So you just use this trick, you introduce this x squared plus x squared. But then nothing doing, we tried and we saw that we are not being able to factorize. We are not being able to factorize. So since we are not being able to factorize, so we say that fx is irreducible. So you can say that this is, both conditions are satisfied. It is like no factorization is possible and roots don't belong to this value of L2. So that is why we'll call it a primitive. So like there is no higher meaning here. It's just a definition that this is a primitive polynomial. And ultimately, essentially, any general polynomial in value of L2 can be broken into, it's like prime numbers, like factors, like any number can be broken into product of prime factors, right? So similarly, any polynomial in value of L2, you can break it into products of primitive polynomials. So that's kind of the idea. Does this make sense? So if you're not being able to break into further factors, it means that it is itself a primitive polynomial. Like prime numbers, if you're not being able to further, prime numbers cannot be factorized any further, right? So it's same kind of logic is there. Is it clear now?
Yes, sir. So it is not, since it is not factorizable, so it is not primitive, no?
No, since it is not factorizable, that is why it is primitive.
That is why it is primitive. Okay.
Yeah, so I mentioned, right, there are two conditions. So both have to be satisfied. So it is not factorizable, and in this case, and roots also shouldn't belong to 0, 1, essentially. 0, 1, neither of them should be roots. If you can show both of these, then it is a primitive.
Then it is a primitive.
Yeah.
Now it is one condition is satisfied, it is not factorizable, but another
Yeah.
condition 0 and 1 should not be root. That is
Yeah.
not satisfied, no?
That is satisfied, right? I just wrote it here, right? You have 1 plus x cube, you put 0, you get 1. You put 1, and with both 0 and 1, you are not getting zeros, right? You can just do it and see. Yeah. So both are not satisfied. So sorry, both conditions are satisfied.
So it is primitive.
So it is primitive. Yeah.
Okay.
You have to check for both of these conditions and then like answer.
Yeah. Okay, sir. Yeah. Okay. Thank you, sir.
Okay. So now let us now understand the working and how to do the mechanical kind of calculation of these codes. Some questions that are relatively simple, so I'm not going there. Okay. So now we'll talk about M sequence generation. Generators, right? So you are given, so for M sequence generations, you will need, so these need primitive polynomials. If you don't have a primitive polynomial, you cannot generate a proper M sequence. So that is why this notion, you need to check if whatever polynomial you are using, if it's primitive or not, right? So one primitive polynomial, let's say you are given that your primitive polynomial that you are using is some 1 plus x cube plus x to the power 4. So you can check and see this is also a primitive polynomial. And you are asked to show the feed forward. So this polynomial is implemented in like this writing it as some of capital. It's implemented in hardware using registers. So you have to show the feed forward shift register representation, right? So how do you do that? So this is your input. So you implement these polynomials using delay lines, right? So first you have some input line coming I, right? And so that corresponds to 1. So 1 corresponds to input line I. Then you have delays. So after every delay, your power, your exponent power. So this input line is 1, that is x to the power 0. So after your delay, you will have, let's say x1, which corresponds to this output is x1, which actually corresponds to, like in polynomial notation, if you have capital X, I'll just draw it first. So, so this corresponds to x to the power 0. We don't have any term for x, capital X. So I'm just noting it as 0 dot x, right? Plus 0 dot x square. So you have nothing for x and x square. So after first delay, you actually get from 1, you get x, there is nothing. Essentially, I'll come to what I mean here. X2. Let me just fully draw it first and then I'll discuss. This is called X4. So this is the sequence that you have because it's a 4-degree polynomial because you are having up to x to the power 4. So it's a 4-degree polynomial. So for 4-degree polynomial, you will have to input 4 values. So there will be 4 like kind of inputs, x1, x2, x3, x4. But anyway, so you'll have 4 values. So and these are all implemented using delay lines. So this is 1 corresponds to the input. After one delay step, you will get x. After another delay step, you will get x squared. After another delay step, you will get x cube. After another deleted, you get x to the power 4, right? And you're asked what is the correct representation of this output. So let us see which lines are added together. So the input line is added always, right? So we need to, for addition, we need to use adder circuit. So let us draw a plus here, right? Actually not here, to discuss why. So we need an added circuit. Let us draw it here. Why? Because see, what are the things that are being added? Firstly, the input line. So we'll connect the input line to the added circuit, right? But anyway, so essentially these two are added, x3 and x4. So x cube and x to the power 4 are added. So this is, after 3 delay lines, we get x to the power 3. So we'll add this and we'll add this. And so the output of these two will feed into the input. So these two will be added and fed to the input. So this is how you kind of implement this kind of a polynomial using shift registers. Is it clear? And just revise again. It's a 4-degree polynomial, so you will need 4 delay lines, one after the other, consecutively. And so input comes in the first delay line, and you get output x1, which corresponds to capital X. Then you get output x2 corresponding to x square. Output x3 corresponds to x cube. Output x4 corresponds to x to the power 4. And so you have a plus sign with x3 and x4. So you need to draw an adder, and you have to add x3 and x4. You have plus sign correspond to x cube and x4. So you have to draw an adder and add x cube and x3 and x3 and x4, and then feed it back to the input. So this is your feed forward shift register representation. Is this clear, like the mechanics of it? What you need for question is ultimately mechanics, and like further details you can study on your own. But I hope screen is visible. Right? You might have to swipe up by yourself in this Zoom whiteboard. It's not a very good interface, but yeah, I'm using it because I'm facing some bug with the other, with OneNote, which I normally use. Is this clear? If this is not clear, then there is no point proceeding forward. Okay, I hope this is clear. So yeah, if this is clear, then you are told that, let's say, initial sequence is, so in this generation of sequences, these are pseudo-random sequences.
Sir,
So
1 minute. Sir, 1 minute.
yeah,
So what is the input I actually here?
input I, so it is just the input line. So you usually typically start input I with 0.
Okay.
So you are given this initialization. Let's say initialization is 1, 0, 0, 0. Right. So initially you are given x1 is 1, x2 is 2, x3 is x1, x2, x3, x4 is 1, 0, 0, 0. And your input line is initially always 0. And then you do the mechanics further, right? So just give me a minute. So for this, actually you need to draw a table like this. I, x1, x2, x3, x4. So what is the initialization? 1, 0, 0, 0. And then there is an output. So essentially what you are, so the question here is, what is the sequence being generated? Sequence being generated. So the sequence you are actually gathering from the output. So this is your output, which is nothing, which is same as x4. So whatever x4s you are getting is your sequence, right? whatever exports you are getting, it's your sequence. Just give me a minute. Okay. So what is the sequence that you are getting an output? That is the question, right? So, how do you solve this? So first step, we don't know the input initially, and first step, and in first step there is no output also. So let's say write this as output. So there is no output, there is no input. Initially, actually, so you are saying what is this input, then you will just see in a moment that this will get populated afterwards. So initially there is no output sequence. And so after time delay of 1, what happens is there is a shift. So all of these are feed forward shift registers. So they move their input to their output after a delay of 1. So at t equal to 0, if some bit is input, at t equal to 1, it will go to output. So in the next step, what will happen is, right, in the next step, you will actually tap the output. So you will get 0 as output. And then your x3 will go to x4. So whatever is x3 now will become x4 after 1 unit delay. It just moves forward. Similarly, x2 becomes x3, x1 becomes x2. And from the drawing, what will x1 become? X1 will be one second. There is some noise. Can somebody mute themselves? Okay. So x1, x4. So there is one shift. So you can see that there is a shift. Sorry, this is my bad. This is 1. I made an error. This is 1. And so now what will come in place of x1, right? What will come in place of x1? Let us understand this. So here, in the previous step, so whatever is x1 now was I in the previous step, right? So what was I calculated in the previous step? It is x3 plus x4. That goes to I. So we have x3 and x4. Actually, we can do this thing. We can introduce another column. So let's say this is sequence. And then so we can introduce another column which is sum. Which is sum. What is the sum that we have to compute at every stage? It is x3 plus x4. So x3 plus x4 is 0 plus 0, it is 0. And so this 0 is calculated at t equal to 0. And then after 1 delay unit, computation time is very minimal, let's say. So after 1 delay unit, this I goes to x1. So this sum actually 0 goes here. Is this clear? That like there is a feed forward shift register which shifts x1 to x2, x2 to x3, x3 to x4. x4 goes to the output. So your sequence starts with 0. So this is your output. And this sum that we are calculating, x3 plus x4, is going back to x1. My bad. This is not good. Right. So now we'll again do the same thing. Let's shift this here, shift this here, shift this here, shift this here. So second output we know is 0. And now let us compute sum, which is x3 plus x4. x3 plus x4 sum is again 0. And then the 0, we move it to x1. Right? I hope this mechanics is clear. So x3 plus x4 goes to x1 in the next step. And so again in next step, let us see. Right? So let us compute sum now. Again, x3 plus x4, now it is, this is 0 plus 0 was 0. This is now 1 plus 0. So now this sum is 1. And in the next step, this 1 will come over here in x1. And then this goes to 0, this goes here, this goes here, this goes here. And so the next output is 0. Sequences. Remember, we are reading the output from this part. We are reading the output from here. We are reading the output from the end, from x4 basically. So then over here, what will be the sum? x3 plus x4 is 0 plus 1, which is again 1. Right? My bad. Again 1. So let's bring 1 over here and move all of these. The same process. So now the next output is 1. So now the next output is 1. And what is the sum? Again, x3 plus x4, 0 plus 0, that is 0. So we move 0 over here, and again this goes here, this goes here, this goes here, this goes here. Next output is 0. Sum is x3 plus x4, which is 1. Right? This is 1. So input line is typically just left disabled, but you can initialize I with something. So that will be a seed. And you have seeds for random generation also, right? In random numbers. So your I is the seed value. It typically is not initialized. So anyway, so this is a very mechanical process, as you can see. Now the sum is 1, x3 plus x4. So these are the two quantities that we are adding up, 0 plus 0. Now the sum is 1, sum is moved to x1, and then these shift forward by 1 unit. So output is again 1 more 0, sequence is 1 more 0, and then sum is again x3 plus x4, so it's 1 plus 1, binary arithmetic, 1 plus 1 is 0, right? And then you move 0 to x1 and shift everything here, 1, 0, 1, 1. And then again you have x3 plus x4, which is 0 plus 1. Your output is 1. So 0 plus 1, your sum is 1, and you move 1 over here, 1, 0, 1, 0, 1. So again, output is 1. And x3 plus x4 is this and this, which comes out to be 1. So you move 1 to x1, and then x1 moves to x2. My bad. Made a mistake. x1 moves to x2, 1. x2 moves to x3, x2 moves to x4, x4 moves to the output, and then you are calculating again 1. So 0 plus 1 is 1. And output is 0. So let us see this now. So this will actually just so you can see this is the sequence, and you read the sequence from top to bottom like this. So your sequence value, so you'll be asked in exam question, what is the value of the output sequence? And you will have to match, let's say from MCQ, 4 options. So you will answer it by reading this. So your answer will be something like, so you'll try to find out which option matches the best. So in this case, your answer will be something like, if you see any option with less than 3 zeros. So initially you can see that in this sequence, you see that there is 0, 0, 0 followed by 1. So immediately at this stage only you can rule out all responses that have less than 3 zeros. Then you see there is a 1. Essentially, then you can see there is a 1 and there is a 0. So some responses might have 0, 0, 0, 1, 1. So those get ruled out. And so you pick the best option, essentially. Once you have figured out how to do this mechanics, then matching the answers is not difficult. Is this clear? Any doubt? No. All that is there is working of shift register, that like it will just shift the value from input to output after one time delay. So that is all there is. Any questions?
So, sir, X4 is the output, na?
X4 is the output, yes. X4 and
Yeah.
output are actually the same. Like,
Yeah.
but like first initialization you won't take. Like you will take it after some one time delay.
Sir, one thing, in the sequence, why you do not consider the last one for X4, last row of X4?
1 second.
Last row, the X4, that is 1 actually, but you have finished at 0 just before that row.
1 second. 1 second. Yeah.
Is it repetition or something?
Last row.
Maybe start of repetition.
Where? 1 second.
Actually, the last row X4, that is 1 actually.
Sorry, output. Actually, in response to the previous question, output is actually X4, but like after 1 unit delay. So you can see that X4 moves to the output after 1 time delay. And then your question was the last one here.
Last one,
I mean, this will continue, right? I mean, I don't know if it will repeat or not. So,
most probably from this bit it is start repetition, most probably.
Yeah, most likely it will repeat. These are pseudo-random sequences. But
actually, if you continue the loop, then most probably it start from this person.
Yeah, it will most likely repeat after the phone. So but like, yeah, I think you don't need to like you just need to match your MCQ answers. So I think at some point you will be able to, cross out whatever is not matching.
One question is that how up to how much step I have to go for the sequence actually.
So that depends on the options provided, right? If the options are tricky, then you have to like, let's say you have one option as like if the paper setter has given one option as like 0, 0, 0, 1, 0, 0, 1, 1, 0, and another option is 0, 0, 0, 1, 0, 0, 1, 1, 1. So that means even up till this point, you don't know which of these two options are true. You have to do till this bit, and then you can choose option 1.
Yeah. Okay.
Does that make sense? Because like, yeah, so it depends on the options, right? It depends completely on the options. It depends on the option. So you have to check and see. But if the options are simpler, then maybe like at 0, 0, 0, 1, 0 itself, you kind of found that, okay, one of these matches the pattern, and so you write the solution.
Sir, how we are getting initial sequence 1, 0, 0, 0?
So that is provided. That will be given in the question.
Okay, that will
I
be
could
given
have-
in the question. Okay.
Yeah, I could have given anything. No, just
Okay. Okay.
normally it's 1000. We usually, but that is always
Okay.
given in the question. Because you need initialization to be able to, do all this, right? You need to know what the initialization is. This is
Okay, sir.
yeah. Just repeat that. Okay, you just first step you have to do. So first step you have to kind of draw this diagram correctly, which is the shift register diagram, and then draw the diagram correctly, and then you can kind of just follow the diagram and do the mathematics accordingly.
So
Sorry.
how this diagram will be there, sir? In different case, how it will change?
So it depends, right? If you have x3, x cube plus x4, so you will take these two lines, x3 and x4, and add them and feed it to the input. If it was something different, if it was like x plus x4, then you will have to take the corresponding two lines, this line, and add them. If it was x2 plus x4, then you have to take this line or x1 plus x3, then you have to take this and add. So it all depends on like.
So here it is x3 plus x4 given in f of x.
Yeah.
So you have added x3 and x4.
Yeah. X
Okay,
cube and x. Yeah.
And 1 plus x cube. Sir, it is not x cube, na? X3, na?
Yeah, actually, so see, this is like the previous this notation 1 plus x cube plus x to the power 4. This is the mathematical notation. This is the kind of, if you do maths, this is how you will do it. But if you have to implement it in a hardware in register, you do it in this way. So these are both are actually the same.
Okay.
So for every power, so I was explaining, right? For every power of x, you need to add a delay line. So that is why at x cube level, you will have 3 delay lines before, 3 delay circuits before.
For reaching up to x cube, we will have 3 delays.
Yeah.
Okay. Sir, can you just give some example of another polynomial and then drawing its diagram?
Yeah, like I can just modify this. So instead of 1 plus x cube plus x, let's say you have 1 plus x cube. So for that, what you have to do is, you tell me. So one is just the input line. So you just have to, essentially one indicates that you just feed it back here. Which two should I add? So I have added circuit here. Which two should I add?
So x1, no.
Yeah, x1, yes, and
x1 and x cube.
Yeah.
X cube.
Yeah. So in this case, actually, this is 3-degree polynomial. So I don't need to write x to the power 4. So my output is here. So this is 3-degree polynomial. So this is my output.
Yes, sir.
So something like that. Yeah, that's. Okay. Any other question? Because I think this is like the other questions. If you have any doubts, I'll answer. Otherwise, I think the other questions are very like straight from the text, straight from the lectures. It's all there. You just have to read and write.
Yeah, okay, this is somehow clear, but we have to practice actually. We have to check. This is somehow clear. Okay.
Okay. So if there are no more doubts, I can end the session early today. Yeah, just this needs practice. You can try different sequences, but you have to make sure, as I said, it has to be primitive polynomial. So both of the examples that I took, 1 plus x cube plus x to the power 4 and 1 plus x cube, these were both primitive. Actually, one easy check that you can do is something like something which has just, let's say, even values, like 1 plus x squared plus x to the power 4. This will typically not be primitive. Like, this can be factorized, because if you see that I can just add x plus x over here and x cube plus x cube over here, and this will like factorize out into something like 1 plus x. If you take common, you will get 1 plus x cube, x squared plus x cube. Yeah. So if you just have even powers, then typically you will be able to find a way to factorize. Right. And yeah. So then it won't be primitive. So just like whenever you're practicing, just check if you are actually using a primitive polynomial. That is all. Okay. So I'll stop sharing then, and this workbook will get saved, and I'll make it into a PDF and share. And this session is recorded, so it's fine. Thank you. Yes.